move to the next talk. Which is by Shailesh, who will be telling us about machine learning symmetry. Shailesh, you're sharing your screen. Can you? I think you briefly shared it. If you can share it again.
Can you hear me now?
Yeah, I can hear you. If you want to turn on your video, please feel free.
Okay, just a moment.
Hello.
Hi.
Great. So we are ready. So it's 12:38 now. Let's call it. Yeah. So you have about 45 minutes total. It's recommended you finish in 35-40 minutes. So leave some time for questions. Great. So we'll get started. Shailesh Lal will tell us about machine learning symmetry. So please go ahead.
So I'd like to begin by thanking the organizers for giving me an opportunity to speak here. The talk is based on two papers which we put out with Yang, Hangyu, and whom I guess you know where Yang is one of the organizers. The first paper is with Mohammed Zaid Zaz, who is due to join the University of Nebraska as a grad student, and Shobhajit Majumdar, who is a grad student at City. So this is the topic, machine learning symmetry. And by way of motivation or provocation, I'd like to assert that these two pictures are not the same, although they look like a standard random point cloud scattered over 2D space. But if you kind of stare at it, you can see that there's a mirror image. That's why I drew the grid for your convenience. I mean, there's a mirror image here, and there's a kind of an antipodal reflection here, and you can see that the points are roughly symmetric about that. And indeed, this point cloud was generated to be an even function, and this was generated to be an odd function. And although, like to the naked eye, they look, I mean, if I took away the grid, there would be very little to differentiate them. But a primitive AI is easily able to distinguish between them to 100% accuracy with a very minimal amount of training. So this is the basic motivation behind what I'm going to talk about. That there are structures in very simple objects which are kind of which should be obvious to us but are not, and they're very obvious to AIs. So again, by way of motivation introduction, so why AI in physics? So here's a definition of AI that I pulled off the internet, and I can't credit it because I can't find it again. So apologies to the person who came up with it. So artificial intelligence is basically a machine doing something which, if a human were to do, it would be considered intelligent. And of course, physics or mathematics, and there's no shortage of problems for which the solver would be considered intelligent. So, I mean, here are some examples. There's a phase classification in condensed matter systems or in general quantum field theories, constructing a string vacua for, say, phenomenology or cosmology, or classifying signals in colliders. And in all of these, neural networks are an important framework for these analyses. And I'm going to focus on them exclusively here. So when I talk about AI, I'm not really going to talk about, say, decision trees or support vector machines or anything like that. I'll exclusively be talking about neural networks. So, and again, I mean, why AI in physics? Well, it's a novel methodology for thinking about physical systems. I mean, why should we do it? Because for physics, the conventional methodology for analyzing, say, physical systems or is to provide an algorithm which generates solutions. Now you can do this by hand or you can do this on the computer, but this is what you'd be doing. You'd be setting up some equations and providing an algorithm to solve the equations. But when neural networks essentially approach the problem differently, what you have to do there is essentially provide data about what a solution is and let the AI infer how to arrive at it. And in many cases, it actually outperforms conventional methods by quite handily. So this was an example which came up in newspaper, and this was an example which came up in the academic paper. But yeah, I mean, both cases, it's certainly true that that neural networks do very well compared to conventional methods. And conversely, there is a vast array of mathematical physics tools to analyze neural nets, which I won't be talking about. But yeah, if you are, say, a differential geometer, or there would be, or even if you work in statistics, there would be a lot of interesting problems to solve using on neural nets. So, so what is a neural network? This is somewhat a recursive definition, but a neural network is a network of neurons. So basically what you have is an input layer, which is which is essentially the data that you feed into the neural network. It's fed into neurons and further and further on until you reach the output layer, and some number of outputs are generated. And essentially training the neural network essentially involves tuning the parameters of each neuron, so that if you give it if you give it a fixed input, you get the desired output. And this has to be done iteratively over the entire data that you have, and each iteration is called an epoch of training. By the way, please feel free to stop me. Otherwise, yeah, we could also talk after the talk. Yeah. So so here's a very simple thing. This is essentially like any of these little dots over here. This is one of those neurons. So you can see that it's basically so these are the parameters of the neuron along with a fixed activation function, and essentially this is what generates the output of the neuron. So this little thing over here. The fact that this activation function is nonlinear is essentially what makes neural networks so powerful, and so much more powerful than, say, than conventional machine learning. But I don't have, I mean, I wouldn't be getting into that, but that's basically an off-the-cuff remark. So these are these tunable parameters which would be learned during training. These are called the weights and biases of the neural network. And essentially, the reason why the slide is there is to tell you that if there are very many of these things. So if, for example, a layer has n neurons, it would be entirely standard to have, say, n square parameters in that layer. And it wouldn't at all be surprising to have even a tiny neural network, but when you open it up, it has like 10 to the 5 or 10 to the 6 tunable parameters. And therein lies the rub. So this is, I don't know if this is apocrypha or not, but this is definitely attributed to John von Neumann. And the statement is that if you have 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. And it was realized by these people that this is not an empty threat. This can actually be done. So here's an elephant which was drawn with 4 complex parameters, but 4 parameters nonetheless. So there you are. So it's not really an empty thread. So this is basically essentially the problem of overfitting, which is that a complicated model has more parameters, and more parameters, of course, make it more flexible, but it also give it the tendency to learn rubbish, essentially learn spurious features in the data. So here's an example pulled off a machine learning textbook. So this is polynomial fitting some noisy data with different polynomials. So this is a linear fit, this is a quadratic fit, and this is a polynomial of order 300. And of course, you can see that a polynomial of order 300 has enough degrees of freedom to essentially try and chase as many data points as it likes and fit as close as it likes to them. But I don't think anyone who looks at this curve would consider this to be a good solution to this problem, to this regression problem. And the reason why that is, which is intuitively obvious, is that when you try to evaluate this polynomial, on the order 300 polynomial on unseen data, then you don't really expect it to perform very well. Whereas the order 2 polynomial should perform well. And this is kind of quantified in this heuristic, which is that if you increase your model complexity, you could always drive down your error on the training set on the data that is visible to you. But when you want to evaluate the same model on data that you haven't seen, then usually if the model is too complex, you don't really expect it to perform very well. So this is how essentially this is how you would tackle this problem. Essentially the idea is that is what I said here. You don't want to wind up in this phase, you want to be somewhere here. So really the criterion is that the trained model should perform equally well when you give it some unseen data. So how do you ensure that? You essentially take the data that you have and you partition it into disjoint sets, and you train the model by optimizing parameters on a given subset, and at every epoch you check its performance. You check that the performance is comparable on a set that it is not trained on. So this is called the validation set, for I guess obvious reasons. And so you could look at say some metric like the accuracy of the model, and something like this would be okay, that it's comparable. Something like this, you would say that this is not quite right. The model is clearly performing much better on the data that is available to it rather than unseen data. So this would be a sign of overfitting. And essentially, when you've got your model to behave like this, then you take it and you evaluate on a completely unseen set and see how well it does. So so here's the summary of all that I said. This is essentially to motivate why we are doing these kinds of problems, which yeah. So basically the idea is that neural networks are extremely flexible because they have a large number of parameters, and they have a nonlinearity that is built into them. So essentially they are universal function approximators. I mean, there's actually a theorem which says that if you have a neural network which is wide, which has enough number of neurons, you could basically approximate any function that you want. So this is the upside, that that they can approximate any function, but this is also the downside, that that they can approximate any function. So it's possible to learn very intricate functions which are not obvious to a human, but it's also possible to learn garbage. So the question is that what one would like to do is to identify what a neural network sees when it looks like a data when it looks at a data set. And as physicists, I mean, anytime we want to identify what something is looking at, or we want to study something that we hope that we would understand well independently of a network, the first thing that we might want to look at are like, what are the symmetries of the data set? And that's basically just because they are so much better understood. I mean, if you have symmetries, then you have conserved quantities, you have invariance, your observables are constrained by the symmetry. So this a data set with symmetry, it would be definitely interesting to know that a neural network can actually recognize symmetry in data. So so this is essentially an overview of what I'm going to talk about. Most of the talk would be talking about the work on conformal field theory, and I talk a little bit about what we did on Lie algebras and representations, and then that's it. So what is a conformal field theory? So if you think of d-dimensional Euclidean space with this standard inner product, and the symmetry transformations of translation and rotation, along with scaling and inversions. So these are the three essential symmetries that we're looking at. So if you have translation and rotation, then the theory is said to have scale invariance. And if you have this additional invariance under inversion, then the theory is said to have conformal invariance. So and although this looks very bizarre, of course, as we well know, conformal field theories, they are actually ubiquitous because they are the formalism to describe systems ranging from, say, quantum gravity to phase transitions. And so we would like to machine learn them in this, at least like we would like to see what aspects of these theories can be machine learned. So it's an interesting problem for various reasons. One reason is that they have a lot of structure. So in principle, CFTs could be regarded as being as close to something solvable as we could have. And despite the abundance of structure, I mean, this bizarre symmetry, they're actually ubiquitous because if you're studying quantum gravity or if you're studying water boiling, you would have to deal with the CFT. So, so there are a couple of questions that we'd like to address. The first is about recognizing conformal invariance using neural networks. And the question would be, can we distinguish scale invariance from conformal invariance? The second question would be, given a CFT, what can a neural network infer about it? So in particular, what we'd be looking at is the conformal block expansion of a 4-point function. And this is analogous to a Fourier expansion of periodic functions. So the idea is that you know that a system has symmetry, and you know that a lot of the behavior is restricted by that symmetry, but that doesn't necessarily restrict everything. So so we know that periodic functions should be expandable in a Fourier series expansion that really restricts a lot, but it doesn't tell you what the individual Fourier coefficients are. So you could have any value for those coefficients and your function would still obey, would still be symmetric under your symmetry. So this is somewhat similar to the conformal block expansion of a 4-point function. So I'll be talking about that. And the overarching goal is to ask the question that what is the landscape of conformal field theories like? So again, by way of setting the stage, what is the difference between scale and conformal invariance? Well, if you want to measure things about a theory, a natural thing to measure are the correlation functions. And it turns out that whether you have scale or conformal invariance, the 2-point functions are essentially are the same. It doesn't really care. But at the level of 3-point functions, you start seeing differences. So if you have scalar operators of a given conformal dimension and you have a correlator, this 3-point correlator, then if you have scale invariance in your theory, then this equals the sum of terms, where the only constraint on these terms is that they should, and that these exponents should sum up to the total conformal dimension. But if you have conformal invariance, then the constraint is much stricter. You can't just have any 3 numbers summing up to this. They are actually completely fixed to be these quantities. So this is a consequence of being invariant under inversions. So let's set up the data set. So you set up functions. So on the one hand, you have functions that are scale invariant. So they are constructed as random point clouds with this constraint. And the second class of functions is functions that are conformally invariant. So these are these are random point clouds with this much stricter constraint. And to help the neural network, although it's not strictly necessary, but it does increase accuracy, we don't feed in the conformal dimension, we feed in actually the 2-point function. And you can see that, so here are the training curves, which are kind of analogous to this thing that I drew here. And what I'm evaluating here is the model accuracy, and this is essentially something called the loss function, which is how the neural network trains. The idea is that the loss function tells you is the penalty on the neural network for it being wrong. So the idea of training is to minimize this loss at every step possible. So you can see that the performance of the network is roughly comparable across the train and validation sets. So it seems to be working. And on the test set, which is a set of functions that were not given to it during training at all, we got an accuracy of about 99%. So and now we turn to 4-point functions. As I said, conformal invariance completely fixes 3-point functions up to this number that is unknown, but there's essentially like one term, and with fixed exponents, the number is unknown. But apart from that, conformal invariance completely fixes the function. But it's less powerful for 4-point functions, because you have when you have 4 points, you have this you have the possibility of considering these ratios, which are called conformal cross ratios. They're invariant under conformal transformations. So if you have this function which is conformally invariant, then this function which is then this is also a conformally invariant function. So and this ambiguity we can't really fix from conformal symmetry itself. Both of them are equally admissible. Nonetheless, there is a constraint on conformal functions, and that 4-point functions, that they can be that they are expandable in a basis called conformal blocks. And the question is that can we machine learn this expansion? So what do I mean by that? I'm going to give you an example of the Fourier series, which I talked about, which is much more, which is much better known than the conformal block expansion. The idea is that you have functions which are odd functions, which are periodic. So this is, of course, not the most general Fourier series expansion, but but if you have the symmetry, then this is actually a complete set of functions to expand this an arbitrary function. So so if you have a function that is that has these symmetries, you can always write it in this form. And the questions that we'd like to ask are that can a neural network distinguish an odd symmetric function where a particular mode is absent with a function where that particular mode is present? And so that's the 0th order question. And then you could ask a slightly sharper question, which is that if I give you a function, can the neural network tell me what should be can give me an estimate of the value of a particular Fourier mode, a particular fixed Fourier mode? So here are two. So here's the data set. You considered essentially 2 classes of functions which have a Fourier expansion, but in the first class you have the second Fourier mode present, and in the second class it's absent. So you could see that. So you can see some example plots of these functions. They are both odd functions. This is where it's present, and this is where it's absent. And I'm not really a gambling person, but I wouldn't like to bet on my chances of telling one apart from the other. So let's see how a neural network does. So you could essentially sample, you could set up the data set in much the same way. You basically sample these 2 classes of functions at some number of points, and you give it as 2 classes to the neural network, and then you ask the neural network to distinguish between them. And again, you can see that it seems to train quite well, and you can, again, once you've trained, you can evaluate it on unseen data, and you basically what you obtain is this confusion matrix. So let me just tell you in a second what the confusion matrix is. Again, it's a recursive definition, but the confusion matrix tells you how confused the classifier is. So If the classifier is omniscient and never makes any mistakes, then the confusion matrix would be completely diagonal. So what it tells you is the ijth element of the confusion matrix is the number of elements of class I that were identified to belong to class J by your neural network classifier. So again, I mean, if the classifier were omniscient, this would be completely diagonal. And the more the off-diagonal terms there are, the worse the classifier is. So this, again, is not too bad. And of course, the question is that why is this, why does this work so well? Even though you have this very minimal data and you have a really tiny neural network. So the question is that, are these data sets intrinsically different, and can we actually visualize the difference? So actually that can be done. You can consider this tuple of endpoints and evaluate the function on this tuple. So this function, then f of x, is also an n tuple. So if you do that, then you can think of every function as being a point in an n-dimensional space. And you could do a method called principal component analysis to project down to 2 dimensions, where you can visualize these points. So if you do that, then what you find is that you find this really nice separation. So functions where you have the Fourier mode missing lie in this little clump over here, and functions where that mode is present lie in this clump over here. So you can see that these functions, they very nicely separate into 2 classes. So there is indeed some intrinsic difference between these things. So and similarly, you could set up the same thing as a regression problem. You could feed it functions where you also feed it where instead of feeding it this data, you feed in functions of this kind, and you tell it what the corresponding value of A2 is, and then then you give it unseen functions, and you ask it to predict what the value of A2 should be. And so this is what we did for about 200 functions, and we found that whatever is the actual value and whatever is the predicted value, they are really within a hair's breadth of each other. So you can clearly see that on this graph. So now turning to conformal symmetry, what we'd like to do is essentially the same exercise but instead of for Fourier expansions, we'd like to do it for conformal field theories. So the simplest possible thing that we could do is to consider a one-dimensional conformal field theory where the 4-point function looks like this. And again, the conformal dimensions of all operators assumed to be equal. So this is what the 4-point function looks like. And essentially, so if this were a real conformal field theory, so these are the conformal blocks that are talked about. And if this were a real conformal field theory, then there's actually a symmetry called crossing symmetry, which fixes what the H's should be and what the C's should be. So what I'm going to do for you now is essentially the same thing which we did for Fourier modes, which is to classify this data. And again, the data set is functions that have this Fourier mode present and functions which have this Fourier mode absent. And in this case, they look even more similar to each other. But again, you could set up the same classifier problem and run your neural network. And again, let me emphasize to you that these are really tiny neural networks. Maybe there are 10 neurons in a layer, and there's a second layer with 8 neurons, and that's it. So yeah, so this is what the model accuracy and what the model loss look like. And if you once you're confident that the model is training well, it should generalize well, then you can evaluate it on test functions and you get this confusion matrix. And again, you can see that most of the functions are classified correctly. And you could also do the same thing as a similar regression problem, which is where you feed in 4-point functions, candidate 4-point functions, and you ask it to predict what is the value of a given conformal block coefficient. And you could do that, and again come up with the same plot, and you can see that again it works pretty well. And again, you could ask that, are these data sets intrinsically different? And indeed, it turns out that they are. So again, you have this nice separation into blue and yellow point clouds of these two classes of functions, although they're not as well separated as before, but nonetheless, you really do have a very nice separation. Right. So this is essentially the first part of the talk. I told you about how neural networks identify various symmetries, and the examples that I talked about were discrete symmetries, which is that even odd classifier right at the beginning, and scale versus conformal invariance. It's also possible, as I showed you, that you can extract very fine-grained imprints of symmetry like Fourier modes or conformal block coefficients. And things that I didn't show you that are also possible to do, and the neural network works approximately equally well there as well. You could identify crossing symmetry in correlators. So you could set up functions that are crossing symmetric versus functions that are not, and ask the neural network to distinguish between them. And indeed, the neural network works very well in doing that. And it can learn discrete symmetries in OP spectrums. It can estimate operator twists, which is a regression problem, but it does it very well. And now what I'd like to talk to you about is machine learning computations in representation theory. So again, so since this is a conversation, I thought it's good to start at the beginning. A Lie algebra is essentially a set of operators that are endowed with this product, which obeys this anti-symmetry property. And usually as physicists, what we're interested in are unitary irreducible representations of this algebra. Where the JI operators can be thought of, can be realized as matrices on a vector space, and this product is the usual matrix commutator. And again, what's usually interesting to physicists is the case when the JIs are Hermitian matrices, and they cannot simultaneously be made block diagonal. And these are actually of very, very central importance in particle physics. So here's a way of essentially building and characterizing these representations, which is called the highest weight construction, which is, so let me give you an example of an algebra which is called A1 or SU2, where you have where the only non-trivial commutator is this and permutations of this. And in this case, you can see that none of the operators commute with each other, so you can only diagonalize one of them. And again, as this is a Hermitian operator, its eigenvectors are a basis. And also the eigenvalues are real, so there's an ordering on them. So, and again, I can't show this to you right now, but demanding that the vector space is finite dimensional basically restricts you to the eigenvalues being integers. So it's perfectly well defined to think of the entire irreducible representation to be labeled by the maximal eigenvalue of J3. And so in general, you don't just have one such J3, but if your algebra is more complicated, you could diagonalize, there could be more than one more than one operator that commutes with each other. This is in representation theory, it's called the Cartan subalgebra, and in physics, we often call it the complete set of commuting observables. And in which case, if you have R such generators, then you would have R such integers. Right. So let me talk to you about, let me tell you what we'd like to machine learn about this. So let's consider direct products of such representations. So if V1 and V2 are representations, then the tensor product of these two vector spaces is also a representation. But in general, it's not an irreducible representation. So if you take this tensor product, you can break it down into a direct sum of irreducible representations. And working out this thing has to be done on a case-by-case basis. In fact, so there are software packages and giant books dedicated to being encyclopedia of what the right-hand side should be. And there are no obvious patterns. So like here are these two here are two examples of this tensor product, and at least to me it doesn't reflect any obvious patterns in this. And what so what the grand goal could be machine learning what the right hand side is, but we could do a simpler problem for the moment, which is just to estimate what is the number of terms on the right hand side. And actually even this is not there's no formula for this, and there is no again there's no obvious pattern for this either. So so here's the data set. We did this for all Lie algebras, but I'm just going to tell you about one class of Lie algebras, which is called the AM, and M is going to range from 1 to 8. And then you have these highest weight vectors, which we embed into an 8-dimensional vector by right padding with -1. So, and again, because we need to cut things off somewhere, we consider vectors such that the dimension is less than that the dimension of this vector space is less than 10,000. And you can compute the decomposition length using a Mathematica package called Liart. And then you see that the distribution of lengths is actually heavily skewed. There is this, I mean, most of the distributions are have a very, most of the tensor products have a very short decomposition length, and some of them have like really big one. So these kinds of distributions are usually not very good for machine learning. So it's better to kind of reorganize them and bin them so that you have a balanced data set. So we essentially set up some cutoffs on the distribution length on the length of the decomposition, so that the whole thing so that the class populations are roughly equal. And then we have these 5 classes, and the problem is that we take is to take the tensor product of 2 irreps and ask which of these 5 classes does that belong to. So again, we can do this, we can set up a neural network with the data and give it the data that I talked about before. And then this is what the accuracy and loss looks like. You can see that the accuracy is pretty high, the loss is pretty low, both of which are good. And again, you can look at the confusion matrix because again, so for the case of those binary classifications, it's not so useful a representation, but I really like it as a representation of the accuracy for cases where you have multiple classes. I mean more than 2, because you can just eyeball the matrix and get a sense of how well your classifier is doing. And you can see that, so first of all, it's mostly diagonal, which is good. There are some off-diagonal elements, but the misclassifications are into adjacent categories, which is also not too bad. I mean, so there could be something which is of length 8, which is recognized, which is binned into this class or something like that. So it's not too bad to have it to have the misclassification into adjacent classes. So you could do similar experiments with other algebras. So for example, you could think of so this was a little bit more sophisticated, but you could think of essentially an over under classification, which is that you take the tensor product of 2 representations and ask that is the length over or under a certain number, which you can fix. And you can see that the accuracy is pretty high. It's about 97, 98% in all cases. The confidence of this classifier is also pretty high. Right. So the last thing that I'd be talking about is to estimate branching rules, which and I'll do it for SU5. The question is that you have some representations of SU5. Which of these representations, if you break down if you break it down into representations of SU3 times SU2 times U1, contain bifundamentals times an arbitrary U1 charge. So you can see that, so this is the data set. SU5 representations are again labeled by this quadruplet of integers, and we cut it off at the number 4 because the dimensions already, so if you have 4 filling in the integer 4 in all of these places, then you can see the dimension is already pretty high. And essentially the time taken to do this calculation on Liard increases exponentially with the dimension of V. And if you were to populate all of these things with 10, then just doing a naive extrapolation suggests that it'll take about 20 years for the full decomposition to arrive, and then you can calculate whether that representation is present or not. By then the model might be a little out of date. So anyway, so we collect all of this data, and we train. And actually, this is pretty nice. We train on a very, very minimal amount of data, and we test on most of the data actually. So, and we can get about 88% accuracy, which is pretty decent. So that's it, I guess. What I showed you is essentially how neural networks are able to recognize symmetry in data sets. Say simple discrete symmetries to full-blown conformal symmetry, consequences of conformal symmetry, including very, very fine-grained features of conformal symmetry. And again, very, very small neural networks achieve high accuracy and confidence in giving you estimates of Lie algebra computations. And but what is most interesting to me, and this is something that I'd like to close with, is that neural networks are able to recognize quote unquote typical consequences of conformal symmetry, such as what that given a 4-point function, what is a given, what would be a particular OPE coefficient. That seems very interesting. And what the grand dream is that you could the grand dream is essentially inspired by the success of machine learning and in looking at the landscape problem in string theory. With the numerical bootstrap being available to us, there's a possibility that you could have like a cornucopia of data about CFTs that you could look at, and then you could ask that, given this cornucopia, what can you machine learn about CFTs? And the really, really amazing thing would be that can you visualize the entire CFT landscape like this, which is essentially a representation where quote unquote similar CFTs are clustered together. And similarly, could you do it for Lie algebra representations? So that would be the best possible thing. Let's see how far we get with that. So that's all that I had to say. So thank you for your time.
Thank you very much, Shailesh, for a very interesting talk. If there are a couple of questions, we have time.
Can I ask one?
Yeah, Andre?
Yeah, I had a question on the Lie algebra part. So if there aren't formulas, as far as I know, for these various quantities, but in some cases, for example, for SU5, there are algorithms in terms of Young tableaus.
Yes.
So I'm wondering if you have any sense what your neural network is doing. I mean, is there any way of learning from the neural network how you might actually go about computing this?
That's an interesting question. I don't have an immediate answer to that. It would be interesting to try to like do an analysis along the lines of what people do with say ConvNets or or related networks where you can actually see what the neural network is learning. But we haven't done that yet. So anything that I say would basically be just shameless speculation.
Okay, Fabian had a question.
Thanks for the talk. I wanted to ask about the introduction. So in the introduction, you mentioned that there's a problem of overfitting and you're choosing very, very small neural networks. You said
right.
two layers with eight neurons or something.
Yes.
So the modern approach to avoiding overfitting is to vastly overparameterize your neural network and then make use of this double descent curve where if you show that the training error goes down and the test error goes back up. So if you continue the overparameterization regime, then this test error goes up and it starts going down again, and it even goes lower than it was initially. So
I see.
It shows a very, very large neural networks and then combine this with early stopping. So stopping the training before you have found a local minimum in the loss landscape.
I see.
You typically avoid.
Right. I mean, yeah, that could definitely be useful, especially actually there are a couple of reasons why we didn't go for very deep neural networks. But thank you for that comment. So the first thing is that early stopping is essentially it is a philosophical thing, but it kind of like mixes training and validation accuracy. I mean, you have to basically decide to stop training by comparing your training and validation accuracies. So it's kind of mixes the two sets. But again, this is like purely philosophical, and there's no reason, there's no deep underlying reason why one shouldn't do it. And definitely it'd be interesting to try. The main reason why we didn't go for very deep networks is actually this. Like even to get the data beyond a certain point becomes prohibitively difficult. But yeah, definitely, I think it would be interesting to kind of see if there are ways of bypassing this, maybe engineering some features or deforming the data in some ways. Essentially trying to augment the data. It would definitely be interesting to try things along those lines, and then we could go for deep neural networks. Yeah.
So I mean, thank you very much for the clarification. What I meant by overparameterizing is that you do not increase the data set, you just increase the size of the neural network. If you make the neural network larger, but also your data set larger, in some sense, you're not overparameterizing anymore.
I see.
But this is a limit where you sort of keep your data, you just make the network bigger.
I see. Okay, thank you for that comment. I'd definitely like to look at it more.
Yeah, thanks for the clarification.
Thanks a lot for the questions and the talk, Shailesh, again.